Yeah.
So, but it's also pretty much based on C.
Yeah.
So everything looks like C. But if you take something like Lisp, that's is a completely different structure to it.
Yeah.
So.
Maybe it's like Lisp. Okay, time to start. All right, as you see, I finished grading the exams. I sent you the solution. I didn't think to bring it all today. Let me just talk about the test a little bit. As I expected, 4 and 5 were the things you had practiced the most. So people did pretty okay. There were some calculus mistakes. But other than that, it was okay, except maybe the magnitude of the force on the top plate, which we did in the homework on the drawing the wire, and that threw some people for a loop. Let's talk about that for a second, because that's actually an important thing. You know, we're studying all these topics, and I don't know how it feels to you, but there's at least, and you can tell from the test, there's sort of two sides to what we're studying. There's talking about the material and the meaning of everything, and then there's getting down and dirty with the calculations. And maybe all technical classes are a little bit like that. There's a lot of talking, which maybe goes a little bit over your head because you don't know the stuff yet. And then there's a lot of doing the calculations, which sometimes seems very different from the talking. And the problem is that we need to do the talking to get you started. We need to do the calculations to really get the knowledge solidified. But then we often skip the third step, which is going back to the talking and looking at the solutions and looking at what we've done. So the question when I asked about the stress is really at the heart of what we're doing. For instance, why are we messing around with constitutive equations in the first place? I mean, who cares? They're just these made-up equations that I care about that maybe you don't care about, and that's the end of the story. Except that there is a reason, and the reason is that we may want to calculate, in order to do a design, we may want to calculate the force that a fluid exerts on a surface. So for instance, if we have an extruder and we are using it on an injection molder, we might want to know what are the forces on, let's say, if it squirts out, what would be the force of that jet impinging on the far wall? Or what would be the force if I'm squeezing polymer between two plates? What kind of restraining force, what kind of total effort am I going to need to put in to keep those plates from just moving forward? Okay? So there are stresses that are caused by the fluids, and the question is, what are those stresses and how do they vary with the operating principles of your instrument? And so on any surface, we can calculate the stress of the fluid. So if we have just a random surface, but then we have some flow going by, so this is my wall, we can calculate the stress at any point by the unit normal to that point, to that surface, times the stress tensor at this point near the wall. So the unit normal dotted with the stress tensor is equal to, times the area, times a little piece of area, is equal to the force. If we integrate it over the whole area, we get the total force. So that's the general equation. And this is why we need the stress tensor. The stress tensor is the state of stress at any point. These points out here are interesting if you're interested in what's in the middle of the fluid, but it's very often the stress at the surface that's of interest to us. So the simplest version of that would be like on the exam problem where you have two parallel plates, and I want to know what's the stress on this surface. And so the answer was, well, it's the stress on that surface. And this is a surface, in this case, with a unit normal vector E2. So this was the stress on a 2 surface, and the flow was in this direction, in the 1 direction. evaluated at that surface. And that surface is at coordinate location, x2 is equal to h. And then we can integrate it over this area, but that's just going to give us length times width. So then we get the total force. These are the same equation. Okay? So it's this kind of equation, this kind of question when we ask about the force is really getting to the heart of why we're going through all this effort in the first place. Unfortunately, we get so bogged down sometimes in the calculus and the tensors that we don't remember how to do that part. Now, the other parts, let's talk about the first page. The first question was, why are the invariants important to stress? And what, yeah. Oh, you want to get your test. Brian, here we go. I've been asking about invariants on a couple of homeworks. And the answer, when I ask, what are the invariants and what makes them different, the answer always has been that they are scalars that don't change quantity when you change coordinate system. They're associated with the tensor like a magnitude, like the magnitude of a vector, for instance. And they don't change no matter what coordinate system you use. And so that's really the clue to the answer to this first problem. The reason we care about invariance is because the stress we calculate also must not depend on coordinate system. So for instance, our stress tensor expressions can never have V1 in them, the velocity component V1 in the equation, because V1 is pegged to some coordinate system called 1, 2, 3, and that's an arbitrary choice. So just like it can't have a VR or a V theta in it, it can't have a V1. So it has to only have combinations of coefficients that don't change when you go from one coordinate system to the other. So that was the answer to number one, and the key was that things don't change when you change coordinate system, and that's why we're stuck with the invariants. And there are 3 invariants for a second order tensor. And we haven't discussed this too much, but in shear flow, the first invariant is 0 because it's equal to del dot V, the trace of the first invariant of the rate of deformation tensor gamma dot is 0. And so it's not going to influence the rheology. And it turns out the third invariant that we've defined is also 0. The only non-zero invariant of the rate of deformation tensor in shear is the second invariant, which is related to the magnitude gamma dot. And that's why for the generalized Newtonian fluids, everything is a function of gamma dot. We did well on the second one, which was the material behavior. And then the third one was maybe also conceptual. The generalized Newtonian fluid constitutive equation is given below. Does it predict memory effects? And this was just, I thought it was easier than it turned out to be for a lot of people, but many people got it right. But the answer was, this constitutive equation, I gave you complete credit for saying that it's not a function of time, but it is a function of time, actually. Both the Newtonian and the power law are a function of time, but they're only a function of the current time. Okay? So when the instantaneous deformation is 0, the stress is 0. And so that means there can never be a memory effect. Memory effects are things like during startup, we see a gradual rise or an overshoot. So we've been sketching the generalized Newtonian fluid results, which just stepped up straight up to some plateau level. So this is the generalized Newtonian fluid, no memory. Actually, everybody said it doesn't predict memory, so everybody got that right, but not the explanation. This is a memory effect. So this relates to our overall structure of the course, where we studied Newtonian fluids, which are linear, non-memory fluids, constant viscosity. Then we moved on to generalized Newtonian fluids, which are nonlinear, but they have also no memory in them. And now we've moved on to the Maxwell model, which has memory, but is back to being a linear constitutive equation. So we're eventually going to get to nonlinear memory constitutive equations as we get further into this. Are there any questions about the exam? If you have any concerns that you want to talk to me about, I'll be available after class. Okay. So let's see if we can pick up where we've been going. We've been talking about the Maxwell model. And as I just said, this is a model that has time dependence, memory dependence. And we're looking to predict better the behavior of our materials. So we developed this constitutive model, which is shown here. Is that going to go? There we go. And we also developed it into the integral form. This is the integral form, which is really the version we're going to use over and over again. Now, as you can see, compared to the generalized Newtonian fluid, the math is getting a little bit more interesting. So I'm going to do a few examples using this constitutive equation so that you get the picture. Now, actually, we're going to do a few in the next homework as well. But then as we get up to the nonlinear constitutive models, we're going to see other forms that are in this sort of integral form. So it'll be really good if you get how I'm doing these calculations. So please interrupt me and make sure that you're following how I'm doing the various calculations with this model. Now, we did some already. Let's see if I can find them here. I'm not sure I have the steady shear one. Yes, here it is. Let's see if we can remember how to do a calculation like this one in order to predict what the steady shear viscosity is. So the way this works is here's our model. Whenever we're doing a prediction of material functions, as you showed me on the test, you start with the gamma dot tensor for the particular flow you're interested in. And so for steady shear, we know what the velocity field is, and therefore we know what the gamma dot tensor is. And we can plug that into this integral, and we get 9 integrals, 7 of which are 0, and 2 of which are equal to each other. Okay? So there are 9 different integrals there for the 9 components of stress. We immediately concluded that psi 1 and psi 2 were 0. And there's the remaining constitutive equation with the gamma dot plugged in. And here's the 2, 1 component, which is the only one that's non-zero, equal to the 1, 2 component. So it turns back into a scalar integral. And this, although it's a little complex, it's actually just an integral of e to the x. So that's all we did, is I pulled all the constants out front and I did this integration and evaluating the limits. And I got this result for the stress. I plug it into the definition and I get that the viscosity is equal to the parameter eta naught. Now if I go back to the original constitutive equation, what was eta naught? Eta naught was this parameter that sat in front of the exponential and over the lambda. It maybe makes more sense if you look over here at the differential equation version. Eta naught was the coefficient of the gamma dot. So when this term is 0 anyway, you could sort of see that in steady shear flow you would just get a Newtonian response. And that's what we predicted. We predicted that you get a constant viscosity in steady shear. The other parameter of the model, lambda, doesn't appear in the steady shear at all, but it does appear when we do step-up of step strain, and we did that one already as well. So let's look at that. Our second example was to calculate in the step strain material function. And so we have to use this crazy sigma dot of t. Gamma dot is always known when you're talking about a prediction of the constitutive equation. We have this crazy sigma dot that we have to just follow its rules, and everything is fine. So we now plug this sigma dot into the constitutive equation. There it is. This is the constitutive equation. It needs a gamma dot. We've got it. We plug it in, and everything is 0 except the 2-1 component. So there's the 2-1 component with the sigma dot in there. And then we have to go back here and plug in the sigma dot as a function of time. It's 0 for time less than 0. It's 0 for time greater than epsilon. So we ended up by breaking it up into 3 integrals, 2 of which are 0 because the sigma dot is 0, and 1 is not. Now, the only additional complication of the step strain is there is this limit as epsilon goes to 0. So now we're looking just at this non-zero portion. Here's the non-zero portion. It's got epsilons in 2 places. And we just carry out the calculus. So everything's a constant except for the t prime. Even the t itself is treated as a constant in this integral. And we're going to do a bunch of these integrals, so it's good if you sort that out. So t prime is the variable. Everything else is a constant. So this is like e to the u du. And so I do a little calculation to make sure I don't make mistakes with signs. And it told me that I need to make this look like e to the u du. I have to make this look like du. So du is 1 over lambda dt prime, so I need to multiply by 1 over lambda and divide by 1 over lambda. And now it's e to the u du, so I put that down and then carry out the limits. Found the final answer, and again I have epsilon in 2 places still. So I carry them over here and I take my limit. Turns out I need to use L'Hopital's rule, which says that when you have 0 over 0, you can take the derivative of the numerator with respect to the thing that approaches 0. So the derivative of the numerator with respect to epsilon over the derivative of the denominator with respect to epsilon, and then take the limit again. And it all comes out. So I predicted my stress, and this time lambda does appear. Okay, so in this prediction, both the value of this eta 0 and lambda are important. When I plug them into the relaxation modulus formula, do a little algebra, I get g of t. Now this is interesting, this prediction. We've never seen that before. Here it is summarized. When we look at this, what do we see? We compare it to our original constitutive equation. It says that there's this prefactor, eta naught over lambda, which is the same prefactor that appears in the Maxwell model. And then an exponential decay of some time over lambda, kind of like this, but not quite. Okay? It's kind of like this in that it's some sort of a time over lambda, but not quite the same thing. We're going to see versions of this constitutive equation where this expression is used to rewrite this expression here. I'm going to show you that in a little bit. So the next thing we did was we said, okay, we've made this prediction for step strain. Is it a good prediction? And that's when I showed you this. This is the stress relaxation in linear axes. And this is stress relaxation in log-log axes. And there's the comparison of data and reality. So now the next step is to make this model a little bit nicer. And what we did to do that was to say, and I argued about this on Monday, that what if I break my stress up into different pieces that take account of the relaxation during different times of this curve. So sometimes it's worrying about that relaxation, sometimes it's worrying about that relaxation, and sometimes this one. If I add up those three, then I get the summation of those stresses from 1 to 3 is equal to the stress at the time I'm interested in. So I take my constitutive equation and I say, I'm going to call this the kth contribution, and it's going to look just like the usual contribution, e to the minus t prime over lambda, gamma dot at t prime, dt prime. But there'll be a different value of eta, a different value of lambda for every one of these kth contributions. And then I'm going to sum k equals, let's say, 1 to 3 or 1 to 4 of these taus. So I get minus the summation, the integral from minus infinity to t of this eta sub k over lambda sub k, e to the minus t prime over lambda, gamma dot of t prime dt prime. And the only difference between this expression and what's written on the slide is that I've changed the order of the operation of summation and integral. So I can either take the sum of integrals or I can take the integral of sum. It's no difference. So you do that all the time. Maybe it looks a little foreign here, but if you have integral of cosine theta plus sine theta, d theta, you know that's equal to the integral of cosine theta, d theta, plus the integral of sine theta. This one is the integral of the sum. This one is the sum of the integrals. So I can switch these, and I get this. It's equal to minus the integral of the sum, eta over lambda, e to the minus, etc. So, when I make these kinds of modifications, I'm trying to sound really convincing, but really I'm just making a guess. And so the proof is in actually using those equations to make predictions and then seeing how those predictions match reality. So one prediction we could make is, once again, steady shear viscosity again. Okay? So steady shear viscosity we've done it 1,000 times now. We can take this constitutive model and predict steady shear viscosity. Maybe I'll put that on homework 5, in fact, homework 6. So I'm going to, I think, assign that. So all you need to do is take this constitutive equation, puts the steady shear gamma dot in, and then carry out the integration. The result is given here in the slide somewhere. Maybe not. Yeah, here it is. Here's the answer. The answer is that the viscosity is the sum of the various eta sub k's that are characteristic of the model. Oh, even in here I used 1 to 3. Interesting. I'll instead do the more complicated one, which is the step shear strain. Okay, so let me do that. Let's see if we can do that one together. I want to predict G of stress and strain, which is the step strain modulus, for this new model. This new model is called the Generalized Maxwell model. Tau equals minus the integral from minus infinity to t of the summation, k equals 1 to n, or 1 to 3, whatever, eta k over lambda k, e to the minus t prime over lambda k, gamma dot of t prime dt prime. So how would we start? We have the material function stuff over here on this screen.
Gamma dot.
Right, we need gamma dot. So what's gamma dot for shear flow? So it's not going to be gamma dot not because we're not doing steady strain. What goes here? Yeah, this sigma dot business. If we're not doing steady shear, it's got to be the sigma dot. So right away, we see that we only have to deal with tau 2-1 once again, because everything else is 0. This constitutive equation, even though it has time in it, and it does have memory in it, okay? In fact, going back to this prediction, here's another example of memory. This is a sample that's been strained for a very short period of time, but the stresses go on and on and on and on. Okay? So this model is predicting memory, definitely. This is a model that predicts memory, but it is still proportional to, it still has this gamma dot sitting right there, and no matter what complications we make out front, we're going to multiply them by 0. And so this model will not predict normal stresses. Okay? This will not predict shear normal stresses. So as I said, we're stuck with just tau 2-1 again, which is fine. That simplifies our life. So tau 2-1, which is a function of time, is equal to minus the integral from minus infinity to t of this sum, k equal 1 to n, eta k over lambda k, e to the minus t prime over lambda k, times sigma dot of t prime dt prime. It's sigma dot of t prime because this says, give me gamma dot at t prime. Here's gamma dot for all cases, you know, and it's going back to your first exposure to functions in high school. If you want if you're given f of x equals 3x plus 1, then f of a is substitute the a everywhere there's an x. So if I want gamma dot of t prime, I put a t prime everywhere there's a t. And that includes up here, okay, because this is really what sigma dot is. So everywhere there's a t, which is over here, here, and here, I'm going to make those t prime. So this is really going to follow the exact steps that I just summarized that we did for the single relaxation time. The only difference is there's this summation that we just have to pay some attention to. And it's going to turn out that we're going to switch these orders of the integral and the sum once again to make things simple. So this is equal to 0 for t less than 0. It's equal to gamma dot, which is equal to gamma naught over epsilon for t between 0 and epsilon. And it's equal to 0 again for t greater than or equal to epsilon. So again, this integral goes from minus infinity to t. So it becomes 3 integrals. One from minus infinity to 0. One from 0 to epsilon. And one from epsilon to t. So of course these two are 0. Okay? T less than 0, whatever here is in this parentheses is multiplied by sigma dot, and that's 0. And up here, when t is greater than epsilon, it's also multiplied by 0. So we get tau 1 at time t is equal to minus the integral from 0 to epsilon of the summation k equals 1 to n, eta k over lambda k, e to the minus t prime over lambda k, times sigma dot, which is this constant gamma naught over epsilon dt prime. From here on, it's just calculus, okay? There's not a lot of rheology here. I'm going to switch the order of the integral and the sum because that's how I do integrals. I do them one at a time. So I'm going to sum the integrals instead of integrating the sum. I'll put my minus sign on the left-hand side so I don't lose it. And so it's the summation k equals 1 to n of a bunch of integrals from 0 to epsilon. I'm going to pull out of the integral the stuff that's not a function of t prime. Okay? So eta sub k, lambda sub k, those are not a function of t prime. Those are constants. I don't want to pull them out of the sum because they depend on k, but I can pull them out of the integral. Gamma naught's a constant. Epsilon's a constant. This has a t prime in it, so I keep that. E to the minus t prime over lambda k dt prime. So once again, we've got e to the u du here. Okay? So if u is minus t prime over lambda k, then du must be minus 1 over lambda k times minus 1 dt prime. I'm taking the derivative with respect to t prime, so t doesn't contribute. Minus 1 over lambda k is the coefficient, and then there's another minus 1, and I get that. So this is just like before. I have to put in a 1 over lambda k here. I have to take it out by putting a lambda k there, and I get e to the u du. Equals. Copying all this stuff down. The summation k equals 1 to n. These lambdas are canceling. Eta k gamma naught over epsilon. And now the integral, which is e to the u, the integral of e to the u du is e to the u. So I get e to the minus t prime over lambda k, evaluated from 0 to epsilon. So again, this comes out as before this part. When I put epsilon in for t prime, I get e to the minus t minus epsilon over lambda minus e to the minus, put a 0 in, t over lambda. If I factor out an e to the t over lambda, okay, this is equal to e to the t over lambda, or e to the minus t over lambda k, times e to the epsilon over lambda minus 1. Looks right. Don't think I made a mistake yet. Minus tau 21 equals the summation k equals 1 to n, eta k gamma naught over epsilon. Well, let me put the over epsilon over there. E to the minus t over lambda k times this ratio, e to the epsilon over lambda k minus 1. So we just were reviewing this. This is exactly the same as the previous one. We're going to take the limit as epsilon goes to 0. The numerator goes to 0. The denominator goes to 0. We need L'Hopital's rule. So take the derivative of the numerator with respect to epsilon, and I get e to the epsilon over lambda times 1 over lambda. And the denominator, I get 1. And that limit is 1 over lambda. So this term came from taking the derivative of the numerator with respect to epsilon. And this term came from taking the derivative of the denominator with respect to epsilon. Then I take the limit again, and I get e to the 0 is 1, so I get 1 over. So I finally get my stress. Tau 21 equals minus the summation k equal 1 to n of eta k over lambda k times gamma naught times e to the minus t over lambda k. Now we plug it into the formula for the relaxation modulus, so that means we divide it by gamma naught, and we get g of t. And in principle, it's a function of gamma naught, but it turns out not to be. It's minus tau 21, so that minus sign goes away. And that gamma naught goes away. It's the summation k equals 1 to n, eta k over lambda k, e to the minus t over lambda k. We made up this model by saying that we wanted to take our stress in little bites, and we would generate stress in little pieces, but each piece would be given by a Maxwell model. We say, in principle, they're going to have different values of eta and lambda, and then we'll add them up to get our total stress. Now, we didn't know how that would turn out until we tried it. So we tried it with steady shear, which you're going to do in the homework. And now we've started in step strain, which we just did. In steady shear, it turns out that each of those viscosity parameters adds up to give the total viscosity. We didn't know it would turn out like that, but it did. And each of the g of t's add up to give a total g. Okay, because before we had the single model, the only difference was there were no k's and this sum wasn't there. But it turns out they all just add up. Notice that, well, I already talked about that, excuse me. All right. So now how does this work? Well, if you pick all the same etas and all the same lambdas, you don't get anything different from before. It'll look just like this. But if you pick different heights, which are different etas, and different lambdas, which is different locations of this curvature, you can get your data to fit a curve perfectly, an experimental curve perfectly. So this is an example of data on a polystyrene solution, very typical data. And I picked 4 different relaxation times and 4 different relaxation moduli. So these G sub k are just eta over lambda. So instead of having those 2 parameters, we write it as G. And I picked them very carefully so that they would add up perfectly. Okay, now how did I do that? Actually, I used Solver in Excel. So what you do is you write this function in Excel, and you guess these 8 parameters, okay? And you tell it to minimize the error between the data and the prediction, and you get that result. Okay? It's a little tricky, and I have a handout on the website so that you could see how that's actually done. Now, the truth is that if you just guess garbage here, Solver will never find you a good solution, because nonlinear optimization is tricky. You kind of have to guess good numbers. Maybe you've experienced that already. So what these numbers are, let's take a look at them. There are some very large lambda and some small ones. The large lambda refers to the lambda that goes with this curve that predicts the long time behavior. As we go up in lambda, so from 450 to 100, we picked a contribution that had a larger G and a shorter lambda. But when you add it to this long one, if you just added those 2 together, you'd get something that would look like this with a little ripple in it. Okay? Then when you add the third one in, you get something that looks a little bit like this with a couple of ripples in it, maybe. And then when you add the fourth one, which has the highest G, look at the G's, they're increasing here. Then finally, you get one that goes through all the data. So maybe if you've studied polymers before, maybe you've heard the term longest relaxation time. This fit allows you to calculate the longest relaxation time. And for this material, it's 450 seconds. So the longest relaxation time of a material is the longest time that you would have to wait for it to relax. But this system of breaking up relaxation time shows you that there are shorter relaxation times that determine the character of relaxation at short times. And it's the longest relaxation time that determines the ultimate amount of time it takes to relax. The other thing that's really interesting about this result is that our result shows up in our constitutive equation. So remember that our constitutive equation is minus the integral from minus infinity to t of the summation k equals 1 to n of a to k over lambda k e to the minus t prime over lambda k gamma dot of t prime dt prime. So as I pointed out before, this result is almost the same as that prefactor. In fact, this quantity is just G evaluated for t minus t prime. If you started with a model written as tau equals minus infinity to t, G of t minus t prime, e to the minus t prime over lambda, gamma dot of t prime dt prime. If you started with this model and did the same calculation that we just did, you would get that the relaxation modulus would be equal to whatever this stuff was out front, evaluated at t. So maybe if you think about this model, the generalized Maxwell model, you remember that we got the exponential from the Maxwell model itself, which had that spring and dashpot character. Or we got it from adding up the contributions, and we just picked the exponential because we liked it. So it was arbitrary. So perhaps that gives you some qualms, like she just picked exponential out of the air. And then just now, I just picked to add them up out of the air. And I got a model that fits the data, but it needs 8 parameters to do it. Now, 8's a lot. 8's a lot of parameters. And depending on the relaxation data, you may need 10 or 12 or 14. Okay? So there's a lot of arbitrariness to this model so far. And so we actually also refer to a model that's, in some senses, even more arbitrary, this one. Okay? This model doesn't link us permanently. Actually, I wrote this wrong. This doesn't belong here. Everything, this is correct up here. Everything before the gamma dot. Okay? This model with G of t out front says there's a model that is based on the general idea of the Maxwell model, but we're not going to lock ourselves into the exponentials or sums of exponentials. If you want to do other things with more complicated math in there, if that fits your data better, you go ahead. It actually doesn't matter. Whatever you put in for the math here is going to predict the relaxation modulus, whatever's in the front. So the structure of this model as the integral of a function of t minus t prime times the rate of deformation at t prime will always give, when you put in the step strain kinematics, it'll always give whatever function you put out front. This model is called the generalized linear viscoelastic model. Okay, there it is. The generalized linear viscoelastic model. And this goes back to those springs and dash pots. Okay? Because remember, we picked a spring and a dash pot in series. And maybe if you've looked at those kind of models before in another class, you can imagine a spring and a dash pot, maybe putting a whole bunch of springs and dash pots in parallel as well. So for instance, this was our original model, a dash pot connected to a spring, and we got the Maxwell model. If we put a whole bunch of different dash pots connected to springs, maybe 3 of them, that's the generalized Maxwell model. Okay? Adding them up in parallel like that is like adding up the different contributions that we just did. Now maybe you think, well, that's good, but I think my data does this. Or I think maybe I should do something complicated like a spring and then a different dash pot with a different viscosity, some sort of intermediary thing like that. You can make up whatever you like. You could put another spring down like that. These kinds of dynamic models, you can do anything. All of them have a g of t associated with them. And all you're doing by playing with those springs and dash pots is changing the shape of this curve. So there was a time period in the history of rheology where people published a lot of papers on various different dash pots and springs using their intuition about how those things add up. But all they did was mess around with the g of t prediction. That's all that does to this model. It doesn't change anything else. It will always be a model of this character. Okay? So that's why people now will talk about this model instead. Sometimes they'll still use, very often in fact, they'll still use the sum of exponentials. But fundamentally, it's this general model that has all the same character. It will have a constant viscosity that will be, in fact, equal to the integral of this function. I'll have you do that on the homework as well so that you'll see how that works. You can make this function as arbitrary and interesting as you want, but it won't change the fundamental character of the equation. So we have this is a very useful model. And it's useful for interrelating different linear viscoelastic properties. And I'm going to start on Monday with the small amplitude oscillatory shear calculation, which will give predictions in small amplitude oscillatory shear from this Maxwell model. And what's nice is it predicts slopes of 2 and 1, which is reality. Okay? So working with this model, either in the form of the generalized linear viscoelastic or in the generalized Maxwell, is very useful when you're doing very small amplitude types things or very, very slow flows. In fact, every complex nonlinear model that we use must reduce to this model in order to be considered correct. They'll reduce to different functions here, but they'll all reduce to this general picture. Okay? So we're going to build, starting on Monday, we're going to learn a little bit more about this model by looking at it in small amplitude oscillatory shear and discussing how you can use them to fit data. For instance, you can fit small amplitude data and then predict step strain moduli. Once we've finished discussing this model, we'll be done with linear viscoelastic models, and we can start to move on to nonlinear models. Okay, so we've done inelastic models, the generalized Newtonian fluids. Now we've done elastic models, and then once we're done with this, we'll do nonlinear elastic models. Okay? All right, so Friday, no class. It's a Good Friday, so we're taking that day off. Plus, we had an exam this week. So no class Friday, and Monday we'll start up on small amplitude oscillatory shear.